Hi. Okay, so I'm going to do an example that illustrates how you can end up getting pretty substantial errors while doing Gaussian elimination for LU decomposition. So we'll just jump right in to this example. Let's say we have the pretty simple matrix A equals 0.00001, 3, 2, and 1, and for the sake of illustration, let's pretend for a second that MATLAB has 3-digit accuracy. So obviously MATLAB has more than 3-digit accuracy, but to show you where these type of rounding errors can come from, or how this can be a problem, let's just live in a world where there's 3-digit accuracy. So this would store 3 plus 2 digits following, 2 plus 2 digits following, and this 1 plus 2 digits following. Okay, so if we're going to do the LU decomposition, we would start out with this matrix, which, by the way, is designed to be problematic because we have one entry that's really small compared to all of the other entries. So you can, whenever you start adding and subtracting really small numbers from relatively large numbers, that's exactly the recipe to get round-off error. So to do Gaussian elimination on this, the first thing we do is take row 3 and replace it by row 3 minus the factor between these two. So that's going to be 2 divided by, and this is 10 to the negative 5th, times R1. So if we go ahead and do that operation, we're going to get the matrix. So the first one is the same, so I'm just going to write that as 10 to the negative 5th, 3. That row doesn't change at all. We've designed it so that when you take 2 minus 2 times this first row, that is 0. And when we take 1 minus row 1, so 3 times our factor, which is 2 times 10 to the 5th, this ends up being a rather large number. So we have RU is equal to 10 to the negative 5th, 3, 0, and negative 5, 9, 9, 9, 9, 9, whereas RL is equal to 1, 0, that factor that we calculated, so that's 2 times 10 to the 5th, 1. Our factor or our multiplier. Okay, so that's the decomposition exactly, and if we multiplied L times U, then we would get exactly back to A. Now let's think about what happens if we have this 3-digit accuracy. Well, if we round, this is many more than 3 digits, so if we round that, we would have U, if we were only able to store 3 digits in our computer, this would end up becoming 6, 0, 0, 0, 0, 0, 6 times 10 to the 5th. And if you take our L, which again this is still storing less than 3 digits accuracy, so that's fine, times this U, then we're going to end up with, so in 3-digit precision, this would end up being, the first row is fine, but we'd have 2 and then 0 in this lower term. And obviously this, not only is it not equal to A, which we'd be fine with for some amount of rounding error, but it's structurally different. 1 is nowhere near 0. So the problem here is that by computing our Gaussian elimination or computing our LU decomposition in this way, where our ratio or our multiplier was such a large number, we you know, when we took that large number and subtracted a relatively small number and then rounded, we get something that does not reconstruct the original system at all. And that's sort of the recipe right there for getting these big type of errors. So this motivates what can we do to avoid these type of errors, and is there a way that we could do this calculation so that we don't have these giant multipliers? And the answer is yes, and that's partial pivoting, and I'll talk about that in the next segment of this video.